My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's webinar where we're going to explore how to use graphene-enhanced Raman sensing techniques, which is a really interesting and important topic. I'm extremely happy to have Assistant Professor Shengxi Huang, who is now at Rice University. This is a presentation that I saw while Shengxi was at Penn State. And it was a really, really interesting one, and I thought an important one to share with the rest of the community. And so that's why we're here today. So with that, Shengxi, if you want to go ahead and start your presentation, and then when you finish, we'll get into the Q&A period. So thank you very much for being here and for sharing your expertise.
All right. Thank you very much, Terrence, for the kind invitation and the nice introduction. So my name is Shengxi Huang. It's my great pleasure to be here and share with you some of our work on, as Terrence has said, graphene-enhanced Raman Spectroscopy. But I made the title Designer Quantum Materials for New Sensing Paradigms. So I saw one question, what is the quantum materials here? So here it means 2D material. Okay, so it includes graphene and several other types. So first, let me start by talking about this COVID-19 pandemic. During this pandemic, we have all witnessed the importance of sensing technologies and how they have evolved very fast to accommodate different sensing needs. Currently, the most widely used method for COVID-19 detection is PCR, polymerase chain reaction. It can amplify the genomic material and can achieve very low detection limits. However, the detection time is long. As you can see, it's at least 2 to 8 hours. It also requires specialized staff and equipment, and therefore it cannot be used at point of care. On the other hand, we also have immunoassays for COVID-19 detection. This method utilizes the binding between antibodies and the viruses and can achieve very rapid detection, about 15 to 30 minutes detection time. It can also be used at point of care, and actually you can have home test kits based on these techniques. However, the detection limit for immunoassay is relatively high. So despite these existing detection techniques, we still need better sensing technologies. So for example, if we can have some sensors that have more rapid detection and even remote sensing, these types of sensors can be anchored at different public locations, like in the airports. In addition, the constant mutation of these viruses reminds us again and again it's very important that we keep a global scale monitoring for these devices. So if we can have some sensors with accurate detection, but also portable, we can put these sensors in locations like in the hospitals, airports, schools, even in the farms and wilderness. And these sensors can form a global internet of sensors and give us a close monitoring of the virus outbreak and virus mutation. So now in the case of COVID-19, we actually have a pretty good idea of their biomarkers. We know what to detect when we try to do the COVID-19 test. However, this is not the case for all the diseases. And one of these examples is Alzheimer's disease, or AD. AD currently affects over 6 million people in the US. And in the world, this number is over 50 million. It kills more than breast cancer and prostate cancer combined. Just in 2021, AD costs over $350 billion a year in the US. This is the highest societal cost among all diseases, just after COVID-19. Unfortunately, so far, there's no cure for AD and there is no early diagnosis. So if a patient is diagnosed with AD, he or she is typically already in the late stage, and the disease progression is not reversible. So this is mainly because we still lack a good understanding of AD, and their early diagnosis biomarkers are still not fully identified. And therefore, we will need some sensing technologies to give us early diagnosis of AD. And perhaps more importantly, we hope these sensors can help us to understand the pathology of the disease, to discover biomarkers and even drugs. So what kind of sensing technologies can help us to get a better COVID-19 detection and also to identify the biomarkers of Alzheimer's disease? Well, so if we look look at the molecular sensors, here I have a partial wish list for those sensors. For example, we of course hope the sensors to have high sensitivity, high specificity, high multiplexity, and also with rapid detection. So now if we look at the fundamentals of these sensors, a molecular sensor has two most fundamental components. There's a signal transduction mechanism and there's a sensor material. The signal transduction converts the biosignals into signals we can easily measure, such as electrical and optical signals. The sensor material, on the other hand, interact with the molecule, and upon this interaction, we can either amplify the signal from the molecule or we can change the signal from the sensor material. So this way we can detect the target molecules. So now the question is, what kind of material is a good sensor material? Well, I would argue that 2D material can be a very good candidate because 2D materials are atomically thin and their surface is atomically flat. So they can be very sensitive to anything sitting on their surface. So recently, graphene has been explored for COVID-19 detection and can achieve very high sensitivity. And I think for this audience, I don't need to introduce more about the unique structures of graphene. So basically, these 2D materials will have no damping bonds on their surface, making sure we will achieve very low noise in the sensing signals. And of course, beyond graphene, we have many types of 2D materials in the flatlands. For example, like graphene is sitting over here. And in the UV range, we have hexagonal boron nitride, which will be very important for UV applications. And we also have a family of 2D material called the transition metal dichalcogenide. And many of these family members can be used for visible application. And also mid-infrared is another important range for electromagnetic spectrum. And here we have black phosphorus and several other 2D materials. And beyond these natural 2D materials, we can also make designer 2D materials. So we can artificially make some structures out of these 2D materials. So for example, we can build heterostacks and homostacks of 2D materials. This has proved to be an efficient way to tune lots of properties and to observe novel physics phenomena. We can also try to change their shapes. For example, we can roll them up. We can introduce atomic layer replacement called Janus monolayer. We can also introduce atomic doping and defects. So these have all proved to be useful in altering the 2D material properties, and maybe they can be very useful for sensing applications. So in today's talk, I will mainly discuss two aspects. So first, I will talk about the van der Waals coupling between the molecule and the 2D material. So this is a fundamental but very important aspect when we try to design molecular sensors using 2D material as the substrate. And then I will talk about some real biosensing applications now that we did recently in our group. So first, let's look at this van der Waals coupling. So if you put a molecule on the 2D material surface or on any sensor material surface, there will be van der Waals coupling between the two. So now the question is, can you further tailor this van der Waals coupling? Of course, one method is to apply a vertical gate voltage. And this gate voltage will introduce a vertical electric field across the surface. And this can potentially tailor the van der Waals coupling. Now, this method requires some non-trivial fabrication techniques. So the question now is whether we can make this a little simpler. Well, if we look at the fundamental atomic structure tonight, or TMD, we can see from the side view, there is a layer of transition metal atoms sandwiched between two identical layers of chalcogen atoms like this. So what I want to do now is to replace an entire layer of this transition metal atoms into another layer of transition metal atom like this. So by doing this, I'm introducing an outer plane mirror asymmetry and an intrinsic vertical dipole because of the difference between these two types of transition metal chalcogen atoms. So by doing this, I can introduce a vertical dipole. So this type of material is called a Janus TMD. And the name Janus comes from this ancient Roman god who has two faces. One faces the past, the other faces the future. And the name January actually comes from this Roman god. So now I have this Janus TMD material. I'm wondering whether it can really tailor the van der Waals coupling with another molecule on the surface. So before I study this system, let's just look at a cleaner system. So instead of putting a molecule, I will just put another layer of 2D material on the surface. So now the question becomes, can Janus tailor the van der Waals coupling with 2D materials? Well, in order to study this system, let's first synthesize this material. So we collaborated with Professor Jing Kong's group at MIT, and we synthesized these Janus MOSSE layer and its heterostack. So you can see we started with bilayers of MOS2 and also multi-layers of MOS2. We perform a Janus conversion. So the top layer of sulfur atoms are converted into selenium atoms. Looks like this. So now in the center, you can see we have the Janus MOSSE and MOS2 heterostack. At the outer skirt, we have monolayer monolayer MOSSE. So in total, we obtained 5 types of high symmetry stacking, including AA and AB bilayers and several trilayers. So for these heterostacks, the top layer is MOSSE, and all the bottom layers or the middle layers are MOS2. So in order to check the quality of these heterostacks, we perform Raman spectroscopy measurements, and you can see the signature Raman modes for MOSSE and MOS2. And if we perform Raman mapping and photoluminescence mapping, we can see the conversion is relatively complete and uniform. So now if we look at these Raman spectra again, you can see in addition to these high frequency Raman modes, there are actually some very small modes over here in a very low frequency range. So if we zoom in for the bilayers, we can see there are 2 modes, one at around 22 inverse centimeter and the other one at around 38 inverse centimeter. So these modes actually correspond to the interlayer Raman modes. So in these interlayer Raman modes, the entire layer of the 2D material will vibrate as a whole unit compared to the adjacent layers. So we have interlayer shear modes corresponding to this one and interlayer breathing mode corresponding to this one. So we can understand these interlayer Raman modes using a linear chain model. So in a linear chain model, we can consider the 2 layers of 2D materials as 2 small balls connected by a spring with a force constant K. So in the linear chain model, we know the vibrational frequency can be calculated using this equation. So here M is the reduced mass of the 2 balls. Now coming back to this bilayer 2D material, the van der Waals coupling will be corresponding to this force constant. So we can actually use the vibrational frequency measured using Raman spectra and the reduced mass of these 2 layers to actually calculate the van der Waals coupling strength K. So let's do this. So this is our equation. And here I summarize the frequencies for these interlayer Raman modes. You can see the breathing mode and shear mode over here. For comparison, we also perform the same measurements for the bilayer 2D materials, as you can see over here. So if we just compare their frequencies, we can see there is already a little bit difference. But now we can use this equation to calculate the K, and we can compare the K between the Janus heterostack and MOS2 homostack. So now here's the result. So you can see the delta K are listed over here for shear mode, breathing mode, and also for AA and AB stacking. So now you can discover here is delta K are all positive. So what does this mean? This means the Janus heterostack has an enhanced interlayer coupling strength compared to the MOS2 homostack. Now, these results are remarkable because it is the first time that people have ever seen a van der Waals heterostack has a stronger interlayer coupling strength compared to the van der Waals homostack. So this is actually very exciting results. If we actually look at the literature for other van der Waals heterostack, very rarely do people report the low frequency Raman modes, simply because the interlayer coupling strength is too weak and the low frequency Raman modes are not observable. But we still found a few exceptions. For example, in this work, so this is MOS2 and WS2 heterostack directly synthesized by CVD method. And the authors reported the low frequency Raman modes over here. So now if we use these numbers to calculate the interlayer coupling strength K, and we compare the interlayer coupling strength with bilayer WS2 and bilayer MOS2, you can see the numbers are always negative. And this means the heterostack actually has a lower interlayer coupling strength compared to the homostack. And this is in direct contrast with our Janus heterostack. So as a brief summary, so far we have seen the heterostacking will normally lead to a decreased van der Waals coupling strength. And our observation for the enhancement of the van der Waals coupling strength in the Janus heterostack is intrinsically unique. Fundamentally, this is due to the vertical dipole in the Janus layer. So now we have seen the Janus can increase the interlayer coupling strength, which is very exciting. So our question naturally is whether we can further tune this interlayer coupling strength. Well, of course, the answer is yes. You can already see one solution here. So we can tune this interlayer coupling by changing the vertical dipole direction. So for example, we can make this SS interface by putting this SE layer out on the top. And we can also flip this MOSSE layer by forming this SES interface. So we can still use the low frequency Raman modes to examine the interlayer coupling strength for these two interfaces. And the results are here. So you can see the SES interface have the low frequency Raman frequencies red shifted compared to the SS interface. So the conclusion here now is for the interface SS interface, it will have a stronger interlayer coupling strength compared to the SES interface. And of course, we can change the interlayer coupling strength by some other methods. And you can already see here, if you change the twisting angle between the two layers, you can also modify the interlayer coupling strength a little bit. And actually, if we look at the low frequency Raman spectra for these different twisting angles, you can see when the twisting angles are close to 60 degrees or 0 degrees or 60 degrees, we can actually see two interlayer Raman modes, the interlayer shear mode and the breathing mode. So this is actually an indication of a stronger interlayer coupling strength. But when the twisting angle is kind of between 5 and 55 degrees, we can only see one interlayer Raman mode. So this is an indication of weaker interlayer coupling strength. So here we can see the twisting angle is another tuning knob for the interlayer coupling strength. In addition, the difference between the SS interface and SES interface can also be seen by the charge transfer and photoluminescence spectrum. So we know that if we stack MOSSE layer with MOS2, because of the band alignment, there will be charge transfer between the two. So this charge transfer can actually be seen by the photoluminescence spectroscopy seen over here. So we can see for monolayer MOS2, we can typically see two excitons, A exciton and B exciton. Please note here the intensity of monolayer MOS2 actually should be very high because I divided it by 5 for visual effect. So now if I stack another layer of MOSSE here, you can see the A exciton and B exciton intensities are both reduced, but they are reduced differently for different interfaces. So now we can actually use an equation here called PL intensity ratio. It's defined by the intensity of the A exciton or B exciton in the bilayers compared to the intensity of the same exciton in monolayer MOS2. So we can see the intensity ratio calculated over here, especially for A exciton. The intensity ratio is much smaller for SS interface compared to the SES interface. And this is actually because of a more effective charge transfer in the SS interface because of the stronger interlayer coupling strength. So this result actually matches very well with our low frequency Raman modes. Now these results can also be explained using the DFT calculation. So if we look at the electronic band diagrams, here I show the SES heterostructure. The red dots shows the projection onto MOSSE, and the blue dots shows the projection onto monolayer MOS2. You can see the band structure is essentially the same as the superimposed monolayers. So that means when we form the SES interface, the two layers barely talk to each other and the band diagrams just do not change. But now if we look at the SS interface, the things become dramatically different. So you can see the SS interface, the band diagrams actually change from a direct band gap to an indirect band gap, as you can see over here. So this actually indicates a stronger interlayer coupling strength between the two layers for the SS heterostructure. All right, so these results actually matches very well with our experimental observations. So far, we have seen if we form the bilayers of van der Waals materials, if we perform a Janus conversion, we can introduce a vertical dipole, and this vertical dipole can actually change the interlayer coupling strength. So back to our original question, if we put a molecule instead of a 2D material, can this Janus further tailor the van der Waals coupling with the molecule? So before we actually study this question, we need to answer another question. How do we characterize the interface coupling between 2D material and the molecule? Previously, we used low-frequency Raman modes, but now we can no longer use low-frequency Raman modes, simply because those modes do not exist in the interface between molecule and 2D material. And this is because of the symmetry. But now we can actually use another type of Raman modes, the high-frequency Raman modes, and actually the Raman modes from the molecule itself. Because several years ago, there was a phenomenon discovered called Raman enhancement on 2D materials. So basically, if you put some organic molecules on the surface of a 2D material, you can see the Raman modes of those molecules can be enhanced. So here is an example of a molecule called copper phthalocyanine, or CuPC. You can see when we put this molecule on graphene substrate, several signature Raman modes of this molecule are enhanced. So why do we have such an effect? Well, if we just look at the Raman process for the molecule itself. So the molecule has HOMO and LUMO levels. And if we measure Raman spectra, we shine photons into this molecule. But these molecules have discrete states. So typically, you can only excite the electrons from the HOMO level to a virtual state within these actual electronic states. So the virtual states are metastable. The efficiency of emitting photons from these virtual states are very, very small. So this results in a very low Raman intensity. So the efficiency is actually lower than 10 to the minus 6. So now if we actually have a layer of 2D material adjacent to these molecules, the 2D material will have continuous electronic states, and the Raman process from the molecule can actually utilize the real electronic states in the 2D materials. And in many cases, it can form a resonant Raman condition, and this will drastically enhance the Raman intensity for the molecules. As you can see, one example here. So you can also see from this picture, the actual Raman enhancement will strongly depend on two factors. The first one is the electronic band alignment, and the second one is the coupling strength between the molecule and the 2D material. So these two factors actually constitute the so-called RE2D selection rules. So in specifically, if we put different types of molecules on one type of 2D material, for example, on graphene, we can see the enhancement factors are actually very different from each other. You can see from this column here. On the other hand, if you just put one molecule, for example, CuPC, but you put it on different 2D materials, you can also see the Raman enhancement factors can be very different from each other, as you can see in these Raman spectra. And actually, if I summarize the enhancement factor for one of the CuPC Raman modes, you can see the enhancement factors are indeed very different. So far we have seen that RE2D effect is strongly related to the coupling strength between the molecule and the 2D material. And actually, for the case of Janus TMD, we can see Janus can provide a stronger interlayer coupling strength with the molecule for certain conditions. So the vertical dipole in Janus can indeed tailor the van der Waals coupling with molecules. So, in addition, we can see there is a very interesting effect of charge transfer between the molecule and the 2D material. Because for the molecules with strong RE2D effect, we typically can see a frequency shift in the optical absorption peaks in the molecules before and after the molecules are sitting on 2D materials. So for example, this molecule called PTCDA, you can see it has two absorption peaks over here. But after we put this molecule on graphene, you can see this absorption peak has almost 20 nanometer frequency shift after it's sitting on graphene. On the other hand, if we look at molecules with very weak RE2D effect, we basically do not see such frequency shift, as you can see over here. So now this is the story about van der Waals coupling. And now let me go to the application part. So regarding the biosensing applications, I'm interested in type of high specificity and high multiplexity sensing, because they can enable easy, rapid, and precise detection of various target chemicals in the mixture. So to do this, we need some kind of fingerprints for the target molecules. So Raman Spectroscopy actually provides fingerprints for molecules. However, for intrinsic Raman, it provides very, very low efficiency, as we have discussed before. So the efficiency of Raman is typically below 10 to the minus 6. And that means if you have 1 million photons entering the system, only less than one of them will undergo this Raman process. So the low Raman efficiency actually greatly limited its application in microanalysis. So about 40 years after the discovery of Raman, a technique called surface enhanced Raman scattering, or SERS, was developed. So for SERS, we can use a rough or structured metal surface to plasmonically enhance the Raman signals. And SERS actually increases the sensitivity of Raman by millions of times. However, a big issue for SERS is Raman signals are hardly reproducible. And this again poses a great challenge for real biosensing applications. So in our group, instead of using rough or structured metal surface, we try to use 2D materials, as we have discussed before, to enhance the Raman signals for molecules. So it turns out for some biomolecules, the RE2D effect can be actually very good. So for example, for hemoglobin, if we put it on graphene, we can see the signature Raman modes for hemoglobin compared to the case without graphene. And in my group, we also demonstrated a series of RE2D effects for important biomolecules like Alzheimer's disease-related proteins, some viruses, including coronavirus, blood proteins, and several others. So if we now use this RE2D as a sensing mechanism for biosystems, there are many advantages. So first, it is omniscient towards many molecules because every molecule has their signature Raman spectrum. It also has high multiplexity and high specificity because of the fingerprinting Raman spectrum. In addition, it can have high sensitivity, and actually femtomolar level sensing has been demonstrated. It will also have unprecedented signal reliability and reproducibility, and this is a huge advantage compared to the conventional surface enhanced Raman spectroscopy. In addition, it will be tunable. So here, let me show you another example showing to demonstrate the signal reproducibility. And this is the signal variation measured for hemoglobin on graphene and on silicon. So you can see on graphene, the signal variation is much reduced compared to silicon. We know silicon is already a very flat surface with very mature processing technologies, but still graphene is much better. All right, so now let me show you a few more examples of various biomolecules and their RE2D effect. The first is amyloid beta 42 or A beta 42. This is a kind of protein that's responsible for Alzheimer's disease, at least from people's current understanding. So here we can see the signature Raman modes for A beta 42. And here, our concentration for A-beta-42 is only 60 picomolar. And this is actually similar to the A-beta-42 level in human blood. So that means this RE2D can be promising for minimally invasive and early diagnosis of Alzheimer's disease by just doing a blood test. And the second example I want to show here is this RBD receptor binding domain on the surface of this SARS-CoV-2 virus. So we can see the signature Raman modes over here. And this RBD is actually the key structure for COVID-19 infection. Its structure directly affects the development of vaccines. And actually, the mutation of this structure is the most headache for scientists when the virus mutates. So detecting this RBD structure has an important implication for COVID-19 detection, vaccination, and related technologies. So in addition to a single Raman measurement, we can also scan the laser surface on the material to perform a hyperspectral imaging. So if you have an unknown material, you will identify its composition and their relative distributions. So for example, if you happen to have a Nike in your lab, you can scan its surface and identify what this Nike is made of. But in our lab, we don't have a Nike, but we have some mouse brain slices. So we just took a mouse brain slice, tried to test the Raman's capability to do multiplexity measurements. So by just doing 1 second Raman measurement, we can already identify the concentration of 17 molecules in the brain. And as far as we know, this is the best multiplexity among rapid detection techniques in the molecular level. In addition, we can perform this hyperspectral Raman imaging, and we can identify the spatial distribution for each of these 17 molecules. So here I just showed 2 examples, and this can be important information for brain study. In addition, this technique can be performed in vivo by inserting optical fibers. So now with this technique, we try to see if we can do something for Alzheimer's disease. So from our collaborators, we obtained 2 types of brain samples. They're from the mice with AD and without AD. So, and then we directly perform Raman measurement on the brain slices. For part of our Raman measurement, we attach a layer of graphene on with the brain. So now from the Raman measurement results, we try to compare the signal to noise ratio. So you can see the red bar shows the measurement results with graphene. The green bars shows the measurement results without graphene. You can see with graphene, the signal to noise ratio is much enhanced for different brain regions. So graphene here actually enhances the signal to noise ratio very effectively. So with this very strong signal to noise ratio with graphene, we can further do some machine learning study for these Raman spectra. So my students did a machine learning classification for the Raman spectra of AD and non-AD. So you can see with graphene, the machine learning performance is much better compared to the case without graphene. So the machine learning accuracy, AUC, sensitivity, and specificity are all effectively enhanced. For example, accuracy can achieve over 95% compared to the case without graphene, which is only about 75%. So here we can see graphene-assisted Raman spectroscopy can be an optics-based, simple yet effective tool to identify AD. So this is very exciting results, but we are not satisfied with this simple task of doing machine learning classification. We want to see if machine learning can teach us something more about the disease. So it turns out in machine learning, using a very simple model, SVM, support vector machine, we can identify the so-called spectral feature importance. So this means the importance of each weight number in classifying AD and non-AD. So what's the use of this spectral feature importance? Well, remember, Raman spectra are fingerprints for the molecules. So the spectral feature importance should have a good correlation to the Raman spectra of those biomarkers, right? So let's examine that. Let's first examine the known AD biomarkers. And here I have 4. So these are 4 types of proteins. And here the dashed line shows their peak frequency ranges. So we can first do a peak matching. So try to find out the overlapping frequency range between these peaks and the spectral feature importance. So we can get a peak matching score. We can also directly calculate the cross correlation between the Raman spectra for these biomarkers and the spectral feature importance maps. So we can get a cross correlation score. If these scores are higher, that means these molecules are more important to AD. So actually, these biomarkers all have very high scores compared to a random molecule, which only has a few percentage of scores. So this matches our expectation. In addition, you can see the oligomeric forms always have higher scores compared to the monomeric forms for both A beta and tau. And this again matches our understanding because oligomeric forms are considered more important to AD. In addition, we can use the spectral feature importance and trying to identify some potential biomarkers. So in our study, we identified 3 molecules. You can see their Raman spectra have a high correlation to the spectral feature importance. And actually, other biochemical studies also verified that these 3 molecules are indeed correlated to AD. So now you can see here what we see is the positive feature importance. We can also get a negative feature importance. So positive here means these features are more represented in the AD samples. And negative means these features are more represented in the non-AD samples. So the negative feature importance can also give us some implication of potential drug molecules. So we also try to use the negative feature importance and try to match some molecules. For example, these are the 2 molecules we found, and we also searched the literature and found out these 2 molecules are indeed inducive to cognitive functions. So far we have seen our method can provide a rapid pre-screening of biomarkers, both positive and negative biomarkers. And this study can greatly accelerate the study of AD in terms of diagnosis, pathology, drug development, and therapeutics. In addition, what we did is simply a Raman enhancement technology together with machine learning analysis. So this method can actually be widely applicable to study other types of diseases, biotissues, biofluids, and also human samples. So, for example, recently we tried to use the similar technique to understand this RBD receptor binding domain for SARS-CoV-2 virus. Structure of RBD of SARS-CoV-2 over here. For comparison, we also performed the measurement for RBD of a MERS, another type of coronavirus. So you can already see there are some differences in their Raman spectra, and these differences come from the different protein structures. So we know a protein has 4 levels of structures. In the primary level, there is a chain of amino acids. So the different compositions of amino acid in the SARS and MERS RBDs contribute to the difference in their Raman spectrum. So again, we can use machine learning to analyze these differences. So in the machine learning model, we first did a classification for SARS and MERS RBDs. We can see very high accuracy, over 95%. And now we can obtain this so-called feature importance again. So the feature importance here, you can see there are many peaks, and we can do some analysis over here. So for example, this is phenylalanine. This shows some peaks over here, and it shows peaks for phenylalanine because so that indicates phenylalanine should have a different composition in SARS and MERS RBDs. In fact, if we look at the sequencing results for SARS and MERS RBDs, phenylalanine does have a big difference in their composition. And the similar case goes for tyrosine and histidine, which also shows peaks in the feature importance. And you can also see in the sequencing result, they have a big difference. But now, if we look at this wave number, this corresponds to tryptophan. So this wave number has almost 0 feature importance. So that means the tryptophan composition should be very similar to SARS and MERS RBDs. And indeed, this is the case from the sequencing result. So we know here, Raman enhancement together with machine learning can help us to understand better about the nanostructures of these proteins. So also, if we consider the COVID-19 detection techniques I said before, we have PCR, we have immunoassays. Their detection time is still relatively long, at least 15 to 30 minutes. Can we do it faster? And can we potentially monitor the mutations of those viruses? I would argue that with Raman enhancement and machine learning analysis, we can potentially do the job. So in all of our Raman measurements, the detection is very rapid, below 30 seconds. It's completely label-free. So together with machine learning analysis, there is a potential to identify the mutations of those viruses. In addition to just the surface proteins of the viruses, we also perform our study on the whole viruses. And we actually included more than coronavirus. So we included influenza viruses, real viruses, and many others. So using machine learning, we can achieve high classification accuracy, for example, over 99% accuracy between human influenza A and influenza B, and over 99.8% accuracy in differentiating a coronavirus from other types of viruses. So with these Raman sensing devices, the machine learning model, together with the virus data bank, we can potentially build this worldwide virus surveillance network. It will give us early alarm of a potential virus outbreak and also give us some predictions of future mutations. So with this, I would like to stop here and just acknowledge our collaborators and my students who actually did the job, and also our sponsors. So thank you very much. I'm happy to take any questions from that.
Jing-Zi, thank you so much. And hopefully the audience understands why we were excited to have you do this presentation, because of the implications using this graphene enhanced Raman technique. One of the questions is, can you explain the mechanism for Acer's via graphene versus more conventional metal-based approaches? Why is it so much more enhanced? Is it resonance from highly symmetric graphene structure behaving like an antenna to amplify the signal, right? So I think it's just asking, what is the mechanism for the amplification, if I understood the question correctly.
Right. Yeah. Very good question. Thank you. So for graphene enhanced or other 2D materials enhanced, it's basically because of it constitutes a resonant Raman condition. If you think about the band diagram I showed before, graphene or 2D material actually provides some continuous electronic bands. For molecule itself, it only has discrete bands. So molecule intrinsically will have very low Raman efficiency. But with the continuous electronic structure, the molecule can utilize those electronic structures from 2D material and have resonant Raman condition. So now why we need to use 2D material? Why not some 3D materials and other types of material that have continuous electronic bands? Of course, we can use those materials, but there's another effect. Like, what is the coupling strength between the molecule and the material? For conventional 3D materials, we know the surface is not flat. The surface will have dangling bonds. So actually, the surface electronic structure will be perturbed by those surface dangling bonds, etc. For 2D material, it's dangling bond free and potentially will form a very robust interaction with the molecule. So that's why 2D material, you can typically see this effect very easily. There are also other studies using 3D materials, and I think people also demonstrated we can see those Raman enhancement effect. So this is that. For a conventional surface enhanced Raman spectroscopy, people typically refer to those plasmonic enhanced. So you can have metal nanoparticles, typically gold or silver nanoparticles, and there is a plasmonic hotspot formed between those nanoparticles. So if the molecule is actually there, its Raman signals are plasmonically enhanced. So this is not related to surface interaction or others. It's typically an optics field enhancement compared to the interaction between molecule and the surface.
Thank you. That it's an excellent question, and I appreciate the response that you provided. There's a question here. It's a very straightforward one. Is how to make graphene massively available. And I'll address that one simply because, as the Graphene Council, we represent the entire graphene community, which includes graphene producers as well as end users. And if it's not obvious, it's clear that the material we're talking about here is the true monolayer single atomic layer of carbon. And there are graphene producers that are producing this material in commercial quantities and even in roll-to-roll quantities, and are doing transfer. So on the commercial side of this, which is where the Graphene Council actually has quite a bit of experience, true monolayer graphene material is available widely commercially, and it's being used in a number of biosensing and similar type applications, not using this Raman enhanced technique necessarily, but exploiting some of the same properties for other types of biosensing and biological materials. So if anybody is interested in how to obtain graphene materials from a reliable commercial supplier, that's one of the things that the Graphene Council helps to connect people with, because there is a lot on the market. Not all of it is bona fide, and that's important that you work with a qualified, if you're not making graphene yourself in your own lab. So there's a couple of these questions from several, what type of graphene do you use? How do you introduce samples into practice? Have you tried graphite or mica for comparison? Can you just talk a little bit about the practicalities? And I have another question I want to layer on top of this. First of all, my observation is this is incredibly exciting for all the reasons that you shared, accuracy, speed, sensitivity. This is kind of the holy grail, if I could use that expression, of kind of sensing platforms and what we want to achieve. What do you see, and please answer these other questions all wrapped up, but what are the obstacles to deploying this on a much, much broader scale? What is the difficulty, do you think, in adoption here, if that's something you can speak to?
Sure. So first, have I tried graphite or mica? In principle, you can try those. And there are some practical issues. For example, for graphite, you can see if you put molecule on graphite, then for Raman measurements, you need to, in our Raman measurement, we use the reflection mode. So for graphite, when the laser enters the graphite, typically the light will all be absorbed, so it's fully absorbed. But in our case, we use graphene together with silicon and 300 nanometer silicon oxide. So 300 nanometer silicon oxide actually forms a great optical cavity. It will have multiple reflections. So that actually enables you to see the Raman signals more effectively. The enhancement factor itself will not change, but this just enables you to see the Raman signals more efficiently. For example, you can have a lower measurement time, etc. For mica, honestly, I haven't tried, but I think it's an interesting idea, and maybe we can try that at some point. So what's the obstacles for putting this forward? I would say the system will need to have some further advancements. For example, as I have said, graphene currently, so graphene enhanced or 2D material enhanced, there is a match between molecule and the 2D material. So the molecules I showed, they have strong enhancement on graphene. How about other 2D materials? We don't know yet. I think there needs to be more studies on what is actually a good match between molecule and a 2D material. In addition, for some of those effects that you see, for example, the brain samples, it's not much of an enhancement, but it's more of the effect of noise reduction, which is another important aspect when we try to have good biosensing results. We need to reduce the noise in order to give us good machine learning performance and then good classification. Another obstacle, I would say, and maybe some of the audience and maybe companies here can help, is that I think we really lack a good database for biomolecules, especially for those larger biomolecules like proteins. Maybe this is because the community, the bio community and medical community, traditionally are not very involved with the Raman community. So there's not very consistent data, Raman data for those biomolecules. And therefore, if you want to really match those spectral feature importance with certain molecules, there are lots of difficulties. And we all know for Raman measurement, it strongly depends on many factors: the laser wavelengths, the substrate you actually use, and power, collection time, etc., and also the status of those molecules. So Raman is sensitive to those conditions, which is great for sensing. But I think we need to have some standards when we try to build a database and try to match them with the signals we measure. So I think this is something we need to build over the time.
Absolutely. And, what you just said about, the biosensing community, traditional biosensing community and the medical community, your healthcare side, and our side of carbon materials and these nanomaterials and 2D materials. These are two different worlds that have not crossed very much. We hear that same sentiment echoed from our other companies in the Graphene Council that are active in this field. And the same is to have this library that we need to develop that's non-existent or nascent. So I think that's really, really important, and we will do our best on our side to kind of bring these two worlds together, because there's obviously clear benefit to both sides to doing that. There's a question here that. Well, that's kind of the role the Graphene Council does, and it's a shameless advertisement for ourselves that we really walk across the end. We focus a lot on the end user community, and that does include medical device companies, diagnostics companies, healthcare providers, laboratories, etc., who need to learn about what this material is capable of doing, and then also understand how to manipulate it, because the details count. Obviously, it's very important. And you addressed, I have so many questions. This is such an interesting topic. But you mentioned the importance of resonance in order to get the effect. Is it your experience that the resonance between biomaterials or biological samples in graphene are, let's say, fairly limited, or do you find that the vast majority of the biomaterials resonate with graphene, or how would you characterize that? How sensitive or how limited is the resonance between graphene and these organic materials?
Yeah, so if we look at those resonance effects, so the resonance effect can be demonstrated in several aspects. For example, we know the resonance should strongly depend on the laser excitation wavelength. So that's actually the case. If you change the excitation wavelengths, you will see different enhancement effect, and actually in some excitation wavelengths, you will not see this enhancement effect at all. If you change the graphene Fermi level, if you tune it, you also see a modification of the enhancement factor. So that's why we have. So this basically demonstrates this is a resonant condition. If we look at some bigger molecules, like some large proteins, actually people do not know their homolumo level. So we're basically doing that in a blind way. So if you try to put some molecules on 2D material or graphene, sometimes you can see the enhancement effect, and it does differ for different excitation wavelengths, and if you tune the graphene levels a little bit. But yes, so for larger molecules, there is not a very clear idea of what 2D material we should really use to really utilize this resonant condition to have a really strong Raman enhancement effect. So there needs to be more acceleration, I think, in terms of both experimental part and calculation.
Excellent. I know we're coming up close to the end of the hour, but we still have a lot of questions to go through. Are you okay to stay with us just for a few more minutes?
Sure. Happy to.
Okay. So there's a question here regarding the laser intensity and whether or not it actually alters the biomolecule. Does it fragment it or alter it in some ways? And I did have this same discussion with another colleague of ours about one of the common problems with Raman in the lab is that people are using too high an intensity, higher than they need, and then it does affect the material that they're interrogating. Is that what? How would you respond to that about the laser intensity and whether it affects the molecule and if people are making a mistake by using too high intensity? Is that a common problem?
Yeah, I think that would be a problem, especially if you study 2D material and if you study those delicate biomolecules. So what we do is typically we put the laser power as low as possible and make sure it does not affect the signals. So we do multiple measurements and we see the signals are very consistent. So that means the laser would be safe. Of course, you want to tune up the laser power to the maximum it extends to maintain the molecule or the material, but you want lower collection time. So there's a trade-off here. But I think you really want lower power in order to make sure the material is safe.
Another aspect of Raman is actually where you're focusing the signal on the sample. And one of the comments here is that graphene was placed in Raman spectroscopy. They got one value and then they moved the sample and the value changed. I guess that's about, focus and calibrating. I'm not sure exactly if that's what that particular question is, but
I'm not sure if this is referred to the non-uniform graphene surface. I think you need to have better graphene sample, maybe.
Yeah.
So for example, if you do a mechanical exfoliated sample, if the surface is good, then you should see very uniform graphene signals.
Yeah, I think the quality of the graphene is obviously incredibly important for this, and I think it relates to another question because one of the attendees is asking, what's the advantage of using graphene versus a graphene oxide? Now, if you have a graphene oxide, at least our experience has been, you don't have a perfectly flat surface with graphene oxide, and you have this, these nanoflakes. They're single layer, but I would assume that what we're talking about here is 100% pure carbon, single layer, non-defect, no overlaps, no edges, no holes. You need a perfect sensing platform. Is that not the case?
I would say so. Of course, every material has their defects and non-uniform. There's not a absolutely perfect material. Because if you consider when you do the Raman measurement, you have a laser spot of roughly 500 nanometer to 1 micron, or if you can actually expand the laser spot a little bit. So as long as it's relatively uniform within this 1 micron laser spot, that would be good. And the uniformity would be especially important when you try to understand this mechanism of Raman enhancement with molecules. I would say for some practical applications, maybe the uniformity is not that important. And actually, if you have certain defect structures in graphene or graphene oxide, the molecule may have better absorption on its surface, and that in some cases that may be advantages for this in terms of sensing. But of course, when you try to understand the fundamentals, you really want repeatable results, and it actually gives you what physics is telling you, not what the variation of the material is telling you.
Yeah, I appreciate that. And there's a number of questions I think really relate more to the use of Raman on graphene itself. And I would suggest that maybe a little bit outside the scope of this particular presentation, but I would offer this. Raman is the most commonly used measurement technique to evaluate graphenic material, and that includes graphene oxide and to determine if you have this sp2 bonded carbon. And the Graphene Council is going to have a graphene masterclass, which will include Dr. Charles Clifford from the National Physical Laboratory in the UK and Angela Height-Walker from NIST here in the US. Will be just two of the experts on that. We're going to talk specifically about using Raman in the characterization of the graphene material itself. So that's something to look forward to, and we'll announce that here in the next days. I have a question for you, Professor Huang. We talked about organic materials here, or biomaterials. Can this? And I was fascinated when you showed the example of taking the brain slice, the mouse brain slice, and you did the multiplexing, right? So you ran the signal and you detected all these signals, and were able to identify all the different molecules, right, based on their signatures. That just made me think of so many different forensic type applications that could be used to interrogate, tissue samples and other materials. Can this be used for non-organic or non-biological materials to do this kind of? Because, for example, if we want to look at chemical composition, typically we're using an XPS, but that won't tell you molecules. That'll tell you elements, right? And I thought what was fascinating was this ability to detect the molecules based on their signatures. Could this be, I'm thinking now of things that could be like for food products, or it could be for, other agricultural analyses and such as that, but maybe even soil samples. So inorganic materials. What's the limit of where you think this could be used?
So we choose some organic molecules, and actually not very, very small organic molecules, relatively big, because they themselves have intrinsically their Raman cross-section is not very small. So within a reasonable detection time, you will see the Raman signals, even with the enhancement structure. For very small inorganic molecules, we actually haven't tested them. So I would be interested in seeing the results. I would say one consideration is their Raman cross-section. So for example, like CO2, we didn't test it, and I don't think we can test it using our graphene enhanced Raman technique because their cross-section is too small.
Understood. I think we'll end the webinar here with the questions. I want to thank everybody who's attended. Really appreciate it. We will distribute a copy of the slides. Professor Huang, I want to thank you so much for sharing your time and your expertise with us today. Did you have any closing comments you wanted to share?
Well, I think there are lots of great questions and great comments. So if you are interested, you can get in touch with me and for potential collaborations or further questions. And if you actually work in this area, I would encourage you to explore a little more about what we have discussed. I will be very interested in seeing how the result comes out. So thank you very much, Terrence. It's a great pleasure to be here and interacting with the audience. Thank you so much. Thank you all.
My pleasure. Take care. Everyone stay safe. Thank you for participating.